This code first imports the required libraries for data analysis and machine learning, such as NumPy, Pandas, and Keras. It then imports specific functions from these libraries that will be used in the code, such as min-max scalar for data normalization and layers for model creation. Next, it uses a custom module called callbacks and the OS library to handle file paths and walk-through directories. The code then prints the file path and name for each file in the specified directory. This code reads in a CSV file containing data on Mastercard stock history and assigns it to a variable called df. The data is stored in a tabular format and can be accessed and manipulated through the use of a library called Pandas, which is abbreviated as PD in this code. The read CSV function is used to read in the data from the CSV file, and the file path for the CSV file is specified within the parentheses. In this case, the file path is /cagelput Mastercard stock data latest and updated Mastercard stock history.csv. The code, df.head, is used to preview or show the first 5 rows of the data frame, df. This gives a quick overview of the data and allows for a better understanding of its structure and content. Additionally, it helps identify any potential errors or missing values in the data. This code is commonly used in data analysis and helps researchers and analysts to get a sense of the data before further analysis. The df.tail code is used to display the last few rows of a data frame. This is useful for quickly checking the data at the end of the data frame without having to scroll through the entire dataset. The number of rows displayed can be specified, but by default, it will show the last 5 rows. This is particularly useful for large datasets where it would be time-consuming to check the entire dataset. This code assigns the data frame's index to the date column and converts the date column to date-time format using the pandas to datetime function. Then it drops the date column from the data frame using the inplace parameter to modify the data frame in place instead of creating a copy. Essentially, it is reformatting the data frame's data and removing unnecessary columns to make it more efficient for further analysis and manipulation. In this code, we have 2 lines that create 2 new subsets of a larger data frame, df. The first line, train equals dindex.year 2021 and df.index.year equals 2016, utilizes indexing to select only the rows from the data frame where the index year is less than 2021 and greater than or equal to 2016. This creates a subset of the original data frame containing only data from the years 2016 to 2020. The second line, test equals df.index.year 2021, does something similar but selects only rows where the index year is greater than or equal to 2021. This creates a subset of the original data frame containing only data from the year 2021. Overall, this code is likely being used to split the original data frame into 2 sets, a training set and a test set, to be used for training and evaluating a machine learning model. The training set will be used to train the model, while the test set will be used to evaluate the model's performance on new data. This code first creates a figure with a size of 14 by 8 inches using the plt.figure function. Then it plots the closed column of the train data on the graph with a label of train using the plt.plot function. Next, it plots the closed column of the test data on the graph with a label of test. The plt.legend function adds a legend to the graph, showing which line represents which data. The plt.title function sets the title of the graph to Mastercard close stock price. Finally, the plt.show function displays the graph. Overall, this code is used to plot the train and test data of Mastercard stock prices on the same graph for comparison. This code creates a scalar object named SC that will transform feature values to be within the range of 0 and 1. The scalar object is then applied to the closed column of the trained data frame to transform the values using the fit transform method. This method first fits the scalar to the data and then transforms the data with the fit parameters. The column values are reshaped to be a single column array before being passed into the scalar. This ensures that the data is in the correct format for the scalar to work properly. The transformed data is then stored in a new variable named training set scaled. The first 2 lines of code create empty lists to store values in later. Then there is a for loop that iterates from 80 to the length of a scaled training set. Inside the loop, values are appended to the xtrain list, which contains the previous 80 values from the training set starting at index I, so a sliding window of 80 values. The ytrain list has values appended equal to the value from the training set at the index I. These lists are then converted into NumPy arrays and assigned back to the original xtrain and ytrain variables. Essentially, this code creates a sliding window of 80 values from the training set and uses those values as inputs xtrain and the next value as the output ytrain. This code reshapes the data in the variable xtrain. The new shape is determined by the number of rows xtrain.shape0 and columns xtrain.shape1 of the original data, with an additional dimension of size 1. This means that the data in xtrain will now be organized into this new shape. The code creates a sequential model, which is a type of deep learning model. The model begins with an input layer that consists of a long short-term memory LSTM unit with 50 memory cells. The LSTM unit is used for sequential data, which also includes time series data like stocks. The LSTM unit returns sequences, meaning it takes the output from the previous time step and feeds it into the next time step. The input shape is specified to be the same as the number of features in the training data. After the first LSTM layer, there is a dropout layer, which randomly drops 20% of the connections between the previous and current layer. This helps prevent overfitting, which is when the model memorizes the training data and does not perform well on new data. The code then adds another LSTM layer with 50 memory cells and another dropout layer. This process is repeated one more time. Finally, there is a dense layer with 1 unit, which is used for regression tasks. This layer takes in the output from the previous LSTM layer and produces a single numerical value as the final prediction. The model is then compiled with an optimizer called ATOM and a loss function called MSE, which stands for mean squared error. The metrics to be tracked during training are also specified, which in this case are mean squared error, mean absolute error, and mean absolute percentage error. These metrics help evaluate how well the model is performing during training. The above code snippet creates an early stopping callback object named early stopping, which is used to stop the training process of a machine learning model if it doesn't show any significant improvement after each epoch. This callback takes in 3 arguments: patience, min delta, and restore best weights. The patience argument specifies the number of epochs to wait before stopping the training process. If the model doesn't improve for the specified number of epochs, the training will stop. The min delta argument specifies the minimum change in the model performance that is considered as an improvement. If the change is less than this value, the training will stop. The restore best weights argument restores the weights from the epoch with the best performance. After creating the callback object, the model is trained using the fit method and passing in the callback as an argument. The fit method takes in the training data and target values, as well as other parameters like epochs and batch size. The callback's parameter is used to pass in the created early stopping object so that it can be used during the training process. This ensures that the training stops early if the model doesn't show any significant improvement, which helps in preventing overfitting and reducing training time. This code creates a pandas data frame called history frame using the history object's history attribute. The data frame contains values for the mean squared error MSE, mean absolute error MAE, and mean absolute percentage error MAPE at each epoch of the model training. The code then plots each of these values in separate plots using the data frame's lock function, which allows for selecting specific columns to plot. This allows for visualizing the change in these error metrics over the course of training. This code takes the values from the close column in a data frame DF and assigns it to a variable dataset total. Next, it calculates the length of the dataset total and subtracts the length of the test data frame's close values and 80 from it. These values are then assigned to the variable inputs. Further, the inputs are reshaped into a 2-dimensional array using the reshape function. Finally, the sc.transform function is used to transform the values in inputs based on a predefined scalar sc. Overall, this code prepares the data for further processing by extracting relevant data, reshaping it, and transforming it based on a scalar. This code is creating a variable, xTest, that will store values for the prediction of a stock price. A for loop is used to iterate through a specific range of values. For each value, it takes inputs from the 1st to the 80th index and appends them to the xTest variable. Then, it converts the list to a NumPy array and reshapes it into a specific format that is required for prediction using a machine learning model. The predicted stock price is then calculated using the model and is then inverse transformed using a scaling factor. This final value is the predicted stock price that can be used for analysis and decision making. The first line creates an empty pandas data frame called predictions. Then the second line creates a new column in the predictions data frame called actuals and fills it with data from the close column of the test data frame. Finally, the last line creates another column in the predictions data frame called predictions and fills it with data from the predicted stock price variable. Essentially, this code creates a data frame for storing and comparing actual and predicted stock prices. This code creates a figure with a specific size of 14 by 8 inches and sets the title to Mastercard close stock price. Then it plots the actuals and predictions data from the predictions data frame and adds a label for each. Finally, it displays a legend for the plot and shows the figure. Essentially, this code visualizes the actual and predicted stock prices for Mastercard.